Hello and welcome to another wonderful week of industrial chemistry. So today we're going to be beginning our talk about heat transfer. So before we do this, we need to have kind of an elementary review of some terms. So one of the first important things that we need to remember when you talking about heat transfer is that it's going to be one of the major drivers of a lot of industrial processes. Because it turns out that most industrial processes tend to require a large amounts of heating and cooling. So the classic examples of this are things like metal refining, where you need to push temperatures well above 1,000. But similarly, there's many processes like the cryogenic distillation of air, where you need to send temperatures down below 50 degrees K. So this can actually be quite an intensive process. But before we start thinking about how we can transfer these amounts of energy, the first things we need to think about is how can this energy be transferred? So what we're talking about mostly at this point is going to be heat transfer. So we're looking at raising and lowering temperatures and a little bit less at changes in bonds or internal energy or changes of position in potential energy. So let's focus mostly on this kinetic heat portion. So one of the easiest processes to look at is going to be conduction. So this is essentially the direct transfer of atomic motion from a high energy area to a low energy area. So this is, imagine you take a hot substance like a stovetop and a colder substance like a pot, and so you're going to see a transfer of kinetic energy from the fast moving metal molecules in the stove to the slower moving molecules in the pot. No actual molecules are crossing the border, but essentially you just have uh, collisions from the molecules on the surface to collisions from molecules on the surface. This can also happen in a more liquid environment. So think of a fryer where the hot oil is essentially bombarding whatever food you touch, or from even gases where you can have high contact from a hot gas. But one of the important things is that it does require the materials to be in direct contact. So as soon as I have any degree of separation in between the stovetop and the pot, I'm no longer dealing with conduction. I'm dealing with some other kind of heat transfer. But one of the useful things about this is, again, this can occur for gases, liquids, or solids. So it's a fairly robust sort of method. Next up, we have convection. So this is essentially the heat transfer caused by actual fluids moving. So if I have, say, something like a hot and cold liquid moving through a pipe, the heat is actually being transferred by the liquid itself moving. And so any slower moving liquid will essentially have less possibility to move heat around. Similarly, this is also one of the reasons why in batch reactors we're often going to end up introducing things like stirrers to encourage as much convection movement, or essentially movement of molecules, to get an even temperature regime. And again, this is most frequently seen by most air conditioning units, where I'm not waiting for temperature to slowly move throughout a building by conduction. I actually force hot or cold air through a building through this convection method. So again, this is the idea that, again, any fluid's going to take its thermal energy along with it. And so whenever it contacts another fluid, or even whenever it contacts a solid, it's going to allow a transfer of heat. Now, one of the important things is that this does require a fluid. So you aren't going to have convection with any sort of solids. But it does have a serious benefit of convection tends to move heat a lot more quickly than, say, does conduction. Because it turns out that molecules can actually move much faster than waiting for a cascading series of collisions. However, there is one last form of energy transfer, and that's going to be our good old friend radiation. So this is essentially going to be any sort of heat or energy transfer by electromagnetic emission. and absorption. So more specifically, what we're typically going to be referring to is photons. So if you need a good refresher of radiation, I encourage you to go to PChem 2. So you have anything ranging from black body radiation from hot objects to straight single spectrum radiation, such as you'll find in lights, no matter their spectrum region. Again, UV radiation carrying much more energy than per photon than, say, visible or infrared radiation. But you also have energy that can be transferred through actual fields, such as a magnetic field. And again, one of the advantages of radiation is that it doesn't actually require the presence of a solid, a liquid, or a gas as a transition media. It can even occur through vacuum. However, on the converse side, the media that you're transferring the heat through has to be transparent to the photon region of whatever light is going to be carrying your energy along with. So these are going to be our three major types of radiation. We, due to the shortness of this course, are going to tend to focus a little bit more on the most common but also simplest case, which is conduction. If you really want a good refresher, if you want to know more about convection, I encourage you to actually start looking at some chemical engineering resources, which I can help provide. But unfortunately, that requires a lot more mass transfer than we have the time to devote to in this rather brief class. However, radiation can be a little bit more straightforward, as it requires mostly knowledge that we talked about during physical chemistry too. And so due to its relative simplicity, we're going to tend to skim over it. However, what we're going to be mostly focusing in on is this idea of heating rates, which is essentially just kind of a specialty form of mass balance, because or of energy balance, because we've already been talking about this idea that the heat coming into a system has to essentially balance out the enthalpy entering the system and the enthalpy leaving the system. So again, this is this idea generally of the rate of heat entering the system plus the rate of heat generated in the system, say from reactions, has to be equal to the rate of heat leaving the system plus any rate of accumulation. So essentially any kind of increase in temperature within the system itself. So we can shorthand this to the idea that the flux of heat entering the system has to be equal to the change of flux of heat enthalpy entering or exiting the system. Again, we're mostly assuming isobaric conditions for this. However, what we're going to try and more specifically focus in on through the rest of this section is going to be how do we calculate the heat traveling across a barrier. So we can more or less use our energy balances to figure out what this kind of value is, but what we need to figure out is a little bit more of how do I force this heat to cross the barrier. We're going to focus a little bit more on that next time as we start introducing some ideas of conduction. Till then, take care.